What?
I'll start it.
So does anybody have any questions? Yeah.
So we've talked about like with structural materials that energy is the like primary influence on the price of materials.
Yep, today.
Yeah.
Not 30 years ago, it might have been 50% of it, but today it's 95% of it.
Okay. For like other materials like I don't know, platinum, iridium, copper, zinc, like what are the
Ratios?
or I guess what influences the price? Is there a common trend there or?
Oh, it's still mostly energy because you still got to move a lot of dirt, okay? And the productivity in mining has just exploded in the last 30 years, okay? We used to have people, you know, with shovels in their hands. Now you have great big, you know, earth-moving trucks that will, you know, take something the size. Look, the back of the pickup or the dump truck will take a 2-story house, right? So it still is energy because productivity. The thing is, we're now in a stage where we're seeing productivity growth in the last 50 years that matches what we saw during the Industrial Revolution in the 19th century. Okay, we're in a productivity revolution in terms of manufacturing and productivity. Okay, in the last 35 or 40 years, and everything's sort of flip-flopped because of that. And so, yeah, platinum is still mostly the energy to the ore is so rarefied. You got so much entropy there in terms of it's so dispersed. In order to concentrate it, it takes a tremendous amount of energy. And it's not a lot of labor hours anymore. In the old days when people had to, you know, take 1849 in the San Francisco gold rush, okay? People were sitting there by hand, you know, with little pans, panning for gold. That was a lot of labor content, okay? Well, it wasn't a lot of energy content, it was labor, or if you want, you can say labor is almost energy, but by energy I mean the equivalent of oil, barrels of oil, or, you know, trillions of feet of natural gas, or coal, or whatever. Now we are using energy, the per capita use of energy has just exploded in the last 30 or 40 years, okay? And so we've reduced the labor content of virtually every material. So it's not just steel and aluminum, it's platinum, gold, titanium, you name it. It's still digging it out of the ground and the energy to refine it, get rid of the oxygen and the sulfur and turn it to a metallic state, okay? That's not true of platinum and gold because they can be found almost in a metallic state in nature, but anyway, they're so rarefied. So it still is energy content, but it really is it's a tremendous displacement that I've seen in my lifetime, okay? From 50% of the cost of a material was labor to now it's less than 5%, okay? When I started working, it was 50, for steel it was 50%, now it's about 5% is labor, okay? So just tremendous changes, but that's true in all industries. I mentioned that in the 1980s, the steel industry had like a 4% annual growth rate, which was double the manufacturing growth rate in the United States. And the service industry growth rate was 0. I mean, there was no productivity gain in the services industry, okay, in the decade of the 80s. The mining industry was like 7%. It was almost double the primary metals production. Mining was way ahead of everything else in the world, okay, in terms of productivity gains. Well, you start doing that, you know, 7% productivity over 10 years or 20 years, or even 5% over 20 years, you got a 20-fold improvement. So you take something that was 50% labor and all of a sudden you've dropped it to, you know, 1/10 as much, right? And that occurred in the 1980s and 1990s, and it's created tremendous displacements in the primary metals industries, okay, or in all the metals industries. And then they were all sort of in this great lethargy in the 1980s and 90s, and Wall Street thought, oh, metals are passé, and Ned Thomas, who was department head here, he had the same mentality as all the business school idiots, okay, that thought, oh, you know, less employment means the industry's dying. Well, you know, if you could produce everything everybody wanted in that they needed in a huge quantity with one person, wouldn't that make a wonderful industry as opposed to a bad industry? Okay? Isn't productivity good in the long run? It is good in the long run. Causes tremendous displacement of employment and heartache. I mean, people who started well, let me back up. If in the 1950s and 60s, if you got a job in a company, you could stay there for 30 or 35 years and retire from that company. Okay? That doesn't happen anymore because of the productivity gains in manufacturing. You know, first of all, computer technology, information technology make you a dinosaur within 10 years. You better go into management because you won't know how to do anything useful, okay, within 5 or 10 years, unless you somehow manage to keep up with the technology, okay? But in the old days, you know, your grandparents could start with a company and retire from that company. Very few people can do that today, okay? You've got to be continuously reinventing yourself, okay, in terms of your capabilities. Except college professors, I mean, we just teach, right? We just get up and expound, right? So universities have not changed much in 400 years, okay? And our productivity is about the same as 400 years ago, okay, in terms of number of students we interact with. But anyway, that's going to change too, okay? Yeah, because of videotaping and things like that. I mean, after you think about it, if you're going to teach a calculus course, and there's how many students in the country who need to take freshman calculus every year or sophomore calculus at a university? 2 million? I don't know what the number is, but it's a huge number, okay? And not everybody obviously wants to be a science or math major, but you know, math being sort of fundamental. Well, there's probably only half a dozen really good calculus teachers, right? So why do we have, you know, 1,000 people or 2,000 or 3,000 people lecturing calculus classes, some of whom don't even know what they're talking about, okay? Haven't you had teachers who didn't know what they were talking about? I've had it. One of the advantages at MIT is you have fewer of those. Okay, most of the people, my experience is most of the faculty at MIT actually have a clue, okay? I reviewed a thermodynamics book from another university a number of years ago. The publisher sends it out, you know, it's a textbook that someone had written. And they said, they defined energy as a property that never changes. Really? What they meant is energy is conserved, but to say it never changes, that's the whole study of thermodynamics, is how energy changes from one form to another. Okay? But this was an undergraduate textbook in materials, and they defined energy as something that never changes. Okay? And they defined entropy as something that always increases. Well, wait a second. I mean, if I refine something, I might increase the entropy in the universe, but I decrease the entropy by purifying that to something that was impure before, had lots of entropy, and now it has less entropy. So it depends on what I'm talking about. I mean, there's a concept of a system in there. Well, I mean, and then they had a chapter 5 or 6 that was obviously one of their students' doctoral thesis. Okay, so why are you going to put that chapter into an undergraduate textbook? It's just completely out of place, okay? Didn't fit with anything. It was also totally irrelevant, and I didn't even bother to check if it was right or not, okay? So I panned the book, but it's been published, okay, just because I told the publisher it wasn't worth publishing. And why should you teach something that's wrong that has to be unlearned later? Okay, it's okay to simplify things, because thermodynamics for graduate students is not the same as thermodynamics for undergraduates, okay? But you shouldn't teach things that are wrong that have to be unlearned later, okay? So I'm of the philosophy that there are only certain people who really know how to teach certain things, and we really ought to have something like not that I've ever even looked into University of Phoenix, but the idea that you have courses that can be taken by thousands of people, and the lecture is a very effective lecture, and then you basically go and do recitations. But you know what? You know why that idea will never fly? I mean, I've been pushing it for 25 years around here, but just, you know, falls on deaf ears. You want to know why? Because if you have only the best people lecturing, what happens to all the other professors? They become TAs. And what does that do to their pride? How many senior faculty at MIT do you think would like to be told that you're going to TA this course that's going to be lectured by this guy from Stanford because or this woman from Stanford because they're the best lecturer? Not everyone's a Don Sadoway, okay? But Don Sadoway can lecture better than anybody else in this department. He has a natural gift, okay? If you go up there and look, I mean, you know, Bill Gates told the board of directors of Microsoft that they should watch Don Sadoway's lectures on chemistry. I mean, why is he doing that? I don't know. He likes lectures on chemistry, so, and he's now funding Don Sadoway's startup company, okay? So fine. There's these interesting externalities, but anyway. So did I answer that question? I mean, in a sense, it would be better if someone like Michael Ashby lectured on material selection and Tom Eager just came in and gave a recitation every week or every day and answered your questions. Okay? So anybody have another question? I'd rather answer questions than lecture, okay? Because in fact, you could probably read the book. Okay, and you get the general idea from reading the book, but then you ought to be able to get the insights from someone who has some real expertise. But that doesn't sit with faculty pride. So that's sort of a non-starter until they find that someone's going to figure out a way for the best lecturers to give the lectures and other people just to be the servants. Okay. Not everyone can be the master teacher, right? Other questions? Yeah.
Yesterday we saw that coal is a pretty short supply in the Earth's crust.
Yeah, yeah.
But still its cost per ton is pretty low.
Right, because it's actually concentrated because that's where the forests were. I mean, the coal is located where they had forests. You know, the Amazon, if we didn't cut it down and burn it today, would, you know, 500 million years from now, the Amazon or any other jungle would end up being a tremendous coal reserve. Because what are coals? What is coal other than organics that got buried by geological processes and under heat and pressure it got cooked into coal, right? And there's all kinds of, you start with lignite, which is basically, or peat bogs, okay, which is pretty close to a plant. And then you go to lignite and then subbituminous and bituminous and anthracite. And anthracite's the stuff that was under the highest pressures and the highest temperatures for the longest period of time. And that's the little piece of coal that I passed around. Burns really clean because all the volatiles are gone. Lignite, okay, is still, you know, 50% water, okay? And it's got lots of organics in it, I mean, or volatiles in it. Okay, as you go through that process of different coals, as you go down the chain to higher cooking pressures and temperatures, and then we take some of that coal and we turn it into coke inside an oven, and that makes it even stronger and cleaner burning, except we're burning off all those bad things, and that's what coke ovens give off that the EPA doesn't like, and that's why we let other people in other parts of the world produce the coke, because we ship our pollution to other parts of the world where people would rather eat than have clean air, right? We actually have the luxury of being able to do both because we are more productive than anybody else. And so this is all part of Maslow's hierarchy of needs. Anybody? I've talked about that before, right? So you know what Maslow's hierarchy of needs. We're near the top of that economic pyramid, and so we can afford to be self-righteous and environmentally sound, okay? And we ship all our pollution and lung disease and everything else abroad. But anyway, okay, other questions? No other questions? Okay, well, one of the things that one of the students came up with, I passed this magnesium around the last time, and I don't know if I can put it on there, but they came up afterwards that says, what's that little dot in the bottom, in the middle of this? So if you pass this around, it turns out it's a piece of steel. I just bought these last spring when I was teaching this course, and I decided I ought to have more touchy-feely so people can feel the density of something light, like magnesium, and I couldn't afford to buy a 1-inch diameter, 12-inch long bar of beryllium, which is actually the same density, same weight, roughly the same density. That, I bought it off the web, and it was cheap, and they, convenient, just like this bar of zinc, okay? The bar of zinc is just a piece of cast zinc. I can tell it's cast because of the surface texture. They just cast it in a mold. That is a magnesium anode. I didn't know that until the student came up and asked me at the end of class yesterday. Magnesium anodes are, and we talked about zinc, and the primary use of zinc is as anodes, because magnesium and zinc are top of the periodic table, not periodic, the galvanic series. They are the most anodic of any materials. Okay, magnesium is significantly higher anodic potential and will corrode more easily than even zinc, at least from the thermodynamic potential point of view. And so magnesium and zinc, and actually it turns out aluminum too, are all high energy, relatively high energy content, but magnesium's the best, and so every steel hot water tank in the world has a magnesium anode in it, because the Achilles heel of steel is it corrodes. So if I want to use steel to contain water, I have to do something to protect it from corrosion. Well, I can glass line it, and that's what they do. They take steel tanks and they have this glass they've developed that has the same thermal coefficient of expansion as roughly as steel, and they go in there and they spray it on as a glass frit inside the steel tank, and then they heat it up. It melts, the glass melts against the steel, cool it back down. Since they have the same coefficient of expansion, you now glass line the steel tank. Except the problem is, every now and then there'll be one little spot where the glass didn't flow because of surface tension or some contamination or whatever. And so you go down to Mexico, across the border, to Juarez, right across from El Paso. And an American company has exported the fabrication of these steel water tanks for homes to Maquiladoras in Juarez and other parts of the world. You can't ship hot water tanks very far, but you can ship them to Mexico because that's not too far from the market in the United States. And so they do all this stuff, and then they haven't put the bottom of the tank on, and they have a bunch of Mexican women, because women are more diligent at doing this type of piecework, and they stick their head in there with a flashlight and they look for the gaps in the glass, and they have a little epoxy, and they put a little epoxy on there to repair it. But that doesn't always work, so they stick the designers stick a magnesium electrode like that in there, and it has a steel wire, because if the magnesium completely corroded away, you wouldn't have any electrical circuit left. Okay, so you have a steel wire, and they extruded the magnesium around the steel wire, and they plug that in, stick it down in your hot water tank. And if you go look, if you have a steel hot water tank, I have a plastic one now. I used to have a copper one when I bought the house. Someone wanted to spend a lot of money because copper's a lot more expensive. But if you go and if you have a steel hot water tank and you look at the manual, no one ever reads the manual, right? It will tell you to check, unscrew the electrode on the top of the tank and inspect it every year. And you go ask a plumber if he knows about that, and most of the plumbers say, "What? No one ever inspects their magnesium anode," because usually the holidays in the coating are not so big. They found enough of them. But every now and then there'll be one that's about half a centimeter in diameter, and all that corrosion gets concentrated right there, and within 2 or 3 years you can blow a hole right through that tank, okay? And that creates floods. And I probably put 1 or 2 children through college that way, okay, by looking at these tanks and saying, oh, it corroded. Now, the interesting thing about that magnesium, it is some of the purest magnesium in the world. And it's in this lowly little, and I don't remember the statistics, but like Most of the magnesium in the world is used to alloy with aluminum. Okay? There are a number of aluminum alloys have like 5% magnesium in it. Well, there's a lot of aluminum made. It's second only in metals, so second only to steel. Next most use of magnesium is probably in making ductile iron. You put a little bit of magnesium and cast iron in it. It greatly improves the mechanical properties by changing the carbon flakes to spherical carbon. It's called ductile iron, and you get 10 times the ductility. But the third largest use of magnesium, maybe even second, maybe larger than ductile iron, is in anodes for water tanks. And it turns out if you look at magnesium and, oops, this is neodymium. I was in a rush this morning. But it looks almost the same. But it turns out there is almost no solubility. The specification for the magnesium in that is less than 7 parts per million nickel. Because if you had a nickel precipitate, it will become cathodic and the magnesium anode will just eat away itself. It won't protect the steel. It'll protect the nickel. That's the impurity within it. Because there's a shorter path, electrical circuit path. So it turns out it's a very high quality magnesium in that little piece of magnesium. Very, very, very low nickel. It's virgin material. No remelted alloy recycling in making that stuff. Okay, so that's a long aside on why is there steel wire in the middle of that thing? Because that's the easiest way to buy a 1-inch magnesium rod. Who else wants a 1-inch magnesium rod? What? Sort of useless. In fact, I'll tell you the story right now about magnesium has several Achilles heels. The U.S. Department of Energy has been spending probably $100 million a year since their inception 40 or 50 years ago because they're going to put magnesium in automobiles. Okay, steel is too heavy, aluminum's lighter, but magnesium's even better yet. And so they started putting more magnesium in cars. I mean, it might be 15, 20 pounds of magnesium in an average automobile today. I don't know. I mean, where does it go? Actually, it used to be more. They used to make mag wheels, right? Out of real magnesium. Now what they call mag wheels are usually made out of aluminum. Okay, they might call them mag wheels, but okay, they're aluminum mostly now. Because mag wheels, hey, they got to go through all that road salt in the northern climates, and they corrode. I mean, most of the where's the most of the magnesium found in the world? In the ocean, because magnesium chloride is extremely soluble. There's not a lot of mineral deposits of magnesium. In fact, the only ones are things like the Great Salt Lake. Well, it's just a dried up ocean, right? So that's where you get magnesium, is from dried up oceans. Or you extract it from the ocean. Well, you get it from dried up oceans. It's cheaper than refining it from the ocean itself. But magnesium is so soluble, magnesium chloride is so soluble, that you have to get it from those sources. But so you don't like it anywhere that it's exposed, so you can't even use it for deck lids. That's what they do for aluminum in automobiles. They make the rear hatch door out of aluminum, or they make the deck lid, you know, the hood lid, out of aluminum, because you just bolt those on to the rest of the steel structure and you paint them, and aluminum's got good corrosion resistance and it's just fine. You don't do that with magnesium, because even just a little bit of atmospheric corrosion underneath that and all of a sudden the paint starts flaking off after 4 or 5 years. Okay? Not with aluminum. Aluminum's got better corrosion resistance than steel. I mean, you've seen rusty steel causing the paint to flake off on automobiles, right? Well, what they've done is they've now used galvanized steel and then they paint it, and it'll last 7 or 8 or 10 years. But 30 years ago is one of the biggest problems they had when they decided they didn't want to sell disposable cars anymore. When I was your age, they sold disposable cars. You had to buy new cars every 3 or 4 years. And this was actually a plan of General Motors in Detroit. No one wanted a car that lasted more than 4 or 5 years. They came out with a new model every year, and they were basically disposable. Then the energy crisis of '73 hit, and all of a sudden they wanted cars that lasted 5 years, and then 7 years. And by the 1980s, they were shooting for 10 years. But they couldn't do it because the steel rusted. It's the Achilles heel of steel. What do? They started putting zinc on there. And so for 10 years, I had research out of Detroit on welding of galvanized steel because it was a new material. It wasn't a new material in most industries, but in the steel automotive and painting and welding and everything, they had to learn all kinds of new things to be able to make that. So people, they had people here, I won't mention the faculty members' names, who have been promoting magnesium for many, many years. Joel Clark's first doctoral student looked at the fact that there is a cartel between, there was a cartel between Alcoa and Dow Chemical. After World War II, this was not what I intended to lecture on today, by the way. After World War II, well, there had been a tremendous growth in the aluminum industry. Here it is. This is From Monopoly to Competition, the Transformation of Alcoa, 1888 to 1986, written by a professor at Columbia Business School. And this is comparison of primary aluminum production, thousands of metric tons. So 25,000 tons in the United Kingdom in 1939. Germany actually had more than the United States in 1939. They were in the war, okay? By 1943, look at the United States had grown like more than 5.5 fold. By 1944, they're starting to wind down. They could tell they were winning the war. But the United States rose way above everyone else. So Alcoa became huge, okay, during World War II. This is one of the major transformations. And so this book on Alcoa talks about all this. And then the next page is the great antitrust case, okay? And this was, well, it started in 1911, okay? The Justice Department started looking at Alcoa in 1911. And they initially had them, I said J.P. Morgan, it's Andrew W. Mellon and his aluminum Pierce Arrow, okay? Okay, I mentioned that before. Anyway, it goes on for about 70 or 80 pages about the antitrust. And so George Kenny, who was Joel Clark's first doctoral student about 1976, basically looked at, and he could prove by sales and prices that basically Alcoa, probably Alcan, and Dow Chemical had all agreed after World War II, when the Justice Department was really investigating them and making Alcoa spin off all kinds of things and whatnot, that basically they sort of agreed that Dow Chemical would control the world's magnesium business after World War II. And Alcoa would control the aluminum business, and Alcoa would stay out of the magnesium business. They had the technology to go into it, but they never did. Why wouldn't they do that if 5% of a lot of their alloys were magnesium? Because they were letting Dow control the magnesium business. This was a cartel. All in the wonderful United States where we don't believe in such things, right? Anyway, George had an excellent that really sort of proved it. In any case, there are people who are saying, oh, we're going to put more magnesium in automobiles, but where do we put it? We put it under the dashboard because we don't want any atmospheric corrosion to get anywhere near it, okay? And we also don't want it exposed where people see that it's starting to corrode. So go look under your dashboard of a 10-year-old car, take off the plastic, and you're going to see corroded magnesium. Now, it's still probably fine for holding the wires and the radio and things like that in place, and it will last the life of the vehicle. But magnesium's big Achilles heel is, the first one is it corrodes. And no one's ever solved that problem, except for the people who use it as a corroding material, which is using it as an anode to protect other things from corroding. The U.S. Navy had an interesting application once. They developed a magnesium carbon composite. And people say, oh, this would be wonderful. Lightweight carbon, lightweight magnesium. We'll be able to use this all kinds of places. Well, Ronald Lattanson, the corrosion professor here a number of years ago, he said that when you tried to polish that metallographically, if you were using a water-based polishing solution, it would corrode faster than you could polish. Okay? So you had to use diamond oil-based polishing solutions. Yeah?
I have a question. You said that aluminum has very high corrosion resistance, but it's also very high on the galvanic.
Right. because it has a very protective oxide skin. Okay? Magnesium has an oxide skin, but if there's any chlorides around, it's toast. Okay? Aluminum doesn't like chlorides either, but it's still pretty good. In fact, aluminum has excellent corrosion resistance. We do make ships out of it, okay, small ships and boats, and goes through salt water and it'll last longer than steel. Okay, so aluminum's aluminum oxide. If you use the right aluminum alloy, there are some aluminum alloys that just go to pot, the higher strength ones. Okay, but we make aircraft out of it, and they certainly are out in the air and get rained on when they're down on the ground, not up there. Magnesium oxide's more stable, but when it forms with a chloride, it pits, it delaminates, it just corrodes. Okay, it's not. It prefers the chloride. Magnesium chloride is much more stable than aluminum chloride. Aluminum chloride's not really that stable. Okay, in fact, aluminum chloride, if you react it with water, it generates hydrogen. It just creates HCl and aluminum oxide. I learned this when my oldest son was doing a high school chemistry project, and I can't remember what it was, but I brought back all the chlorides I could think of, and he was going to look at their solubility and stuff. And I took some, I was sitting at the kitchen table and put a little, it wasn't a lot, but I put a little bit of aluminum chloride in water, and I had a little fire there. Okay, generated the hydrogen. Okay, I thought, oh, I didn't realize it's that reactive, because I never really tried it before. But anyway, aluminum chloride's not anywhere near as stable as magnesium chloride, and so it really has to do with relative stability of chlorides and oxides. Aluminum, pure aluminum, has wonderful atmospheric and water corrosion resistance. In fact, one of the companies that was founded by Alcoa was Wherever, you know, the pots and pans, and that's relatively pure aluminum. You start putting copper and other things in aluminum, just like the nickel and the magnesium creates its own little concentration cell, okay, anode and cathode. Copper and aluminum copper alloys are not happy in water, in salt water. So you have to use the aluminum magnesium alloys are actually very good in seawater. So the 5000 series aluminum alloys are good. So you actually have to aluminum corrosion. If you look at the Metals Handbook, the section on aluminum corrosion is much, much thicker than the one on steel corrosion, because aluminum corrosion is a lot more complex. But aluminum has excellent corrosion resistance. We use it for ships, cars. We build sewage treatment plants out of aluminum, because the steel will corrode in 30 or 40 years. That aluminum will be there 100 years from now. Okay? Not because it's lightweight in that case, because it has excellent aqueous corrosion resistance if you use the right alloys. Use the wrong alloys, you're toast. But if you use the right alloys, it's great. Yes? Question over here?
Oh, I was just going to ask, don't we get tired airplanes that fly over ocean routes much sooner than we would?
I don't know if that's true. I do know that typical lifetime of an commercial jetliner is 100,000 hours. Okay, and that time is primarily due to fatigue. Okay, I mean, they've been flying around for 100,000 hours. They got fatigue cracks, and they got so many you don't want to keep on chasing them. Okay, and they're getting to, some of them getting big enough that you don't want to be flying over an ocean, because you could be swimming. Okay, I do know that, anybody remember the Aloha Airlines disaster? Okay, yeah. Okay.
Yeah, there was a hole in the pressure vessel.
Not just a hole, the whole top 2/3. A commercial airline is actually, they call it a ship, like an airship or whatever. It has a keel beam, just like a boat. You start with this great big aluminum beam at the bottom of the aircraft, and you build up from there. You build a structure. So it's sort of like a backbone with a rib cage. So you're lying on your back, and you got your backbone on the table, and the rib cage comes around, and you put an aluminum skin around it. Well, it turns out Aloha Airlines, I always say that the U.S. Navy among the services is the corrosion leader. Okay, they're surrounded by salt water. Okay, Hawaiian Airlines is the corrosion leader, because they're always flying over salt water, right? And what happened in the Aloha Airlines is they also have short flights. You don't fly for 100, 500 miles in Hawaii very often, okay? Unless you're circling a lot, okay? So their flights were averaging 45 minutes. And the fatigue stress cycles were like 45 minutes on average, because it's pressurization of the cabin, depressurization, you know, ground, air, ground cycles, they call them, okay? Takeoff, landing cycles. And the Aloha Airlines, if I remember, I'll find it on a computer and bring it in, a picture of it. But basically they were flying between islands, and the whole top came off, and you could see the seats, and people were strapped in. Only one person died. It was a stewardess who was walking down the aisle. She wasn't in a seatbelt, but they landed. And I remember the first time I ever saw this was like 1980s. Saw a picture of this thing, and I thought, how did that thing stay together? It's because it's got a keel beam in the bottom. Okay, most of the structural strength is this keel beam in the bottom. So what they found is it was corrosion fatigue. And so I'm sure that what you're saying is probably true, but it's really corrosion fatigue. It is fatigue, and it's corrosion fatigue is worse over the ocean. So I suspect that you're absolutely correct, but I don't have the data and I haven't read it. So that's why I said I don't know. Of course, that's a little story in itself. But yes, if you're over salt water as opposed to always over land with a commercial airliner, you will have less corrosion. Okay. And that old story about I don't know is 1985. I walked into my lab, and we had a little whiteboard there, and two of my doctoral students were doing something on the board, and I came in and said, "What are you doing?" And they said, "Oh, we're looking at such and such," and we were wondering, and they asked me some question. I said, "Well, I don't know, but," and I started giving an answer, and they started breaking out laughing. I said, "What are you laughing about?" And they said, "Well, you always, when we ask you a question, you always give an answer." I said, "I don't know." They said, "Yeah, you always say you don't know, and then you proceed to give us the answer." Well, it's not that I'm giving them the answer. I'm a professor. I'm supposed to be teaching you how to think through a problem, okay? And so it's sort of, I handed out the World Trade Center paper. Well, I give that because I think I told you, I spent 3 hours putting that paper together. I've had more comments on that than all other several hundred publications combined. And I sort of wrote that because I was tired of hearing all this stuff that I knew was false. But I really didn't know anything about the World Trade Center. But I did know some basic physics and chemistry. And so I sometimes say, what can you say about something when you know nothing at all about a subject? You can go back to your freshman physics and chemistry. And you can start saying, what do I know? Okay, well, I knew about flames, and I knew about thermodynamics and flame temperatures, and I knew about various things, and that's what I wrote about, okay? And it still stands today, okay? I just got a nice letter from some lady this weekend who was reading it because of the 9/11. You know, we just passed 9/11, and she thanked me for writing this paper, okay? Well, I wrote it because I'd done less work on that than anything else I'd ever worked on, but I wrote it in a way that people could understand, and people like to understand, and anyway. And I wrote about a subject people cared about, as opposed to my research. No one cares about my research, okay? You know, it's too specific, it's too narrow. People want to know about bigger, broader things, which is what I kind of lecture about. Anyway, other questions? Yeah.
So I know that things like magnesium and aluminum are used in, or are being researched to be used in fuel cells.
Are you using for what? I'm sorry. Fuel cells, yep, yep.
Is there corrosion? Do you think
Well, in a fuel cell, you're trying to corrode things, right? You're trying to recombine things and uncombine things and stuff in batteries and fuel cells and stuff. The reason they're using them is because you want a decent voltage, okay? It turns out, if you look at the thermodynamics of some of these things, the voltage, the breakdown voltage of H2O in electrochemical sense is like 1.1, I'm just going to say 5 volts. Anyway, I could just write 1.1. It doesn't take very much voltage to separate hydrogen and oxygen. You probably did that in high school chemistry class, and then you could light a splint and blow up the hydrogen, and you could put a glowing splint into the pure oxygen and burst into flames. Remember doing that? Okay. That only took, you can do that with a, with a dry cell battery if you wanted. Okay, it doesn't take much voltage. For Al2O3, or magnesium oxide, which are two of the more stable oxides, you can decompose those, I don't know, at less than 2 volts, probably less than 1.5, okay? So some of the most stable compounds we have, hey, 2 volts is an eternity, okay, for these bonds. In fact, I was going to talk about that. That was going to be part of my lecture today, was primary bonds and secondary bonds. A typical bond energy, what's the typical bond energy of a primary bond from your freshman chemistry? 1 to 3 electron volts, okay? So all I need is a couple of volts and many of things will decompose, okay? Electrically. What was your question again? I can't remember where I was going. Oh, corrosion in the fuel cells and stuff. So if I'm going to try to make a battery, one of the reasons I use lithium for batteries, if you look at the electrochemical potential, and you learned this in high school chemistry, hopefully, if I want to get the biggest electrochemical difference on the periodic table, I'm going to go from this corner up here to this corner down here. Okay, except no one uses astatine, okay, or polonium, or tellurium, it's toxic, or iodine. They tend to use lithium with something over here. Might be chlorine or something, but you want to go all the way across the periodic table to get the biggest voltages. In fact, if you have voltages between calcium and silicon, there's almost no voltage at all. It's a few tenths of a volt. So they don't want to have a bunch of cells to stack up voltages to get 100 volts or 120 volts. So they want to have only 50 cells to get 100 volts or something, okay? So that's why they're using these very reactive metals, because you want the voltage. And that's one of the problems with Don Sadoway's company. There's probably only 1 or 2 elements on the periodic table that will work for his, he calls it Ambry now, okay? Most of them will give you 2 or 3 tenths of a volt. And guess what your losses are in the resistivity of bringing the current in, okay, in those copper wires or whatever you're going to use? You can lose half a volt. Well, if you're only generating 3 tenths of a volt and you lose half a volt, guess what? It's not a very good power generator, right? You really need something on the order of a volt or 2. A little carbon manganese dry cell batteries, you know, a AA battery, that's 1.5 volts, okay? And that's about the most you can get, because even the most stable compounds, it only takes a couple of volts to break them down. I remember once I used to consult for a company, this division of Johnson & Johnson, and they make medical instruments for all kinds of surgery, and they were, at the time, one of the big things was using electrocauterization. So someone's got an artery, they're doing an operation, and someone cuts through an artery or something, and they want to cauterize that wound, you know, and essentially close up, weld that blood vessel back together. Hey, it's a welding problem, right? They basically would take a tool that had 2 insulated halves. It was basically like tweezers, and it would grab that blood vessel and they apply 100 volts to it. And they were finding the anode, this was 100 volts DC, just locally, and it just kind of dry out that a lot of protein in blood vessels and stuff, and you basically weld it together with the protein and cauterize it. It was electrocauterization. And they said, we're using, we tried everything for our tips. So they started out with stainless steel, and the tips were pitting, terrible pitting on the anode, because that's where the corrosion occurs. The cathode was cathodically protected, no corrosion over there. And they said, we need a better material. I said, what voltage are you using? They said 100 volts. I said, forget it. They said, well, isn't there something we could use? I said, you could try platinum, but it only gives you about 2 volts. You could apply titanium, and it has a pitting resistance of about 5 volts because it has very stable oxide skin. But there's nothing any better. There are limits. In fact, that was supposed to be today's lecture, so we are getting to the lecture. There are limits to the properties of materials, and it has to do with the strength of the bonds. In the case of a fuel cell or a battery, we're trying to use the most reactive things to get the most voltage. okay? And when we don't want corrosion, or we don't want a lot of voltage, we use things that don't have a lot of voltage potential on that galvanic series, okay? Does that answer the question? More or less? Okay. So, where are we? Any other questions? Sort of a recitation again. Last time, material cost is a small fraction of the product cost. Sorry for all you course 3 folks, but material cost is only about 10% of the total product cost. All you mechanical engineers who are in manufacturing and stuff, hey, you got the 90% of the cost. Okay, actually you don't. The management folks have about 30% of it. But you got the inspection and the fabrication and all those other things. Okay? The big costs are in the making the product and shaping it and forming it, which the materials folks can get involved in that if they want. The faster something moves, the greater the value of being lightweight and using magnesium and aluminum. And that's why you get these people in the Department of Energy says, oh, we're going to use magnesium. They have no clue about why they want to use magnesium or how they're going to use magnesium. They're just going to throw $100 million at it every year because a bunch of people say, oh, magnesium's nice and lightweight. Well, thank you very much, but there are a few other properties I'm interested in. Not just lightweight. Density is not the only property that makes a product. Okay, I talked about conveying water, and we talked about, you know, in the old days you might just dig a groove in the ground, and then you might line it with wood, and then you use stone and mortar. Eventually, in the 16th century, they started using lead pipes. Maybe even the Romans used some lead pipes, I don't know. Because it's easy, it's a nice soft metal, easy to form. Excellent corrosion resistance. It'll last for 100 years. The roof of Kresge Auditorium, okay, is lined in lead, okay? Cheaper than copper and has atmospheric corrosion resistance. It'll last forever, okay? In fact, in the old days, the gas tank in automobiles was made out of steel, but steel has lousy corrosion resistance, and if there's anything you don't want leaking out of your automobile, it's gasoline, right? It tends to start fires. So they had turn-coated plate. Since we're talking about corrosion resistance. Turn plate. Almost impossible to find today. I don't even know if there's any steel company still making it. It's lead-coated steel. And you wouldn't use zinc-coated steel because in 10 years that zinc's going to be completely consumed. The lead actually forms a protective lead carbonate on the surface. Okay, first forms a lead oxide, then the lead oxide reacts with the CO2 in the air, forms lead carbonate. That's actually one of the reasons the galvanized zinc in the atmosphere actually is pretty good. It first forms the zinc oxide, and then over time, and then it forms the zinc hydroxide actually almost immediately because there's moisture in the air. But then over about a year, the CO2 in the air reacts with that zinc hydroxide and forms the zinc carbonate, and that zinc carbonate is really what gives you good corrosion protection. The zinc is still protective underneath, but you've got this protective surface oxide of zinc carbonate, just like aluminum has good corrosion resistance because it has a very stable aluminum oxide skin. Titanium is even better than aluminum because it has a very protective titanium oxide skin. Stainless steel is better than regular steel because it has a protective chromium oxide skin. Okay, so some oxides are protective and some aren't, and it's a question of how good. Titanium, actually the best is tantalum. Okay, if you look at the, I can go give my lectures on corrosion, which is not part of this course. Tantalum is better than gold in terms of corrosion resistance. Yes?
So you said that the zinc carbonate doesn't form for some time. It
Takes about a year because there's only 300 ppm carbon CO2 in the air. But if we have more global warming, it'll form faster.
do we
Right?
do any like treatment to form it before we like start using it as a structural material?
Well, that's an interesting question. The answer is I don't know, so now I'll answer the question having said I don't know. Okay. So when my oldest son was doing his Eagle Scout project, we had some, they had some outdoor light posts and some handrails, you know, to some of the steps outside the building at church. And it's a brand new building, and 1986 or so, and all the paint was flaking off. And that's because someone galvanized the steel and then painted it right away. And one of the things that I've since learned is you have to, if you hot dip galvanize your steel, you have to paint it within a few hours before the zinc hydroxide is really formed. Because if you get zinc hydroxide under there, the paint will not adhere to it. And there's some ASTM specs on all this, okay? So they had painted it, and within a year, a brand new building, paint started flaking off. I mean, big chunks of paint. I mean, 1 inch square and bigger. So this became his Eagle Scout project. So I was researching it, and I found, okay, we could have the scouts, and we did. We had the scouts come one Saturday, and they scraped all the paint, and I had sandblasters and everything. So that's what scouts love to work on. You know, give them a chainsaw, give them an axe, and they'll use it. But give them a chainsaw, and they get happy. You know, I mean, they like tools, right? Power tools. So I had them sandblasting and scraping and stuff, and then after that, and I've never found this again, but somewhere I'd found that if you paint it with acetic acid, which, hey, it's just vinegar, right? So I got some acetic acid from Lab Supplies, and we diluted it about 50% or so. And it was nice and smelly, but it was all outdoors, and they were just these buckets of water, and nothing better than a scout with a paintbrush, and he can slop it around wherever he wants, and, you know, acetic acid, you know, get it on your clothes, it's no big deal. You know, it's not like sulfuric that's going to dissolve your clothes. So they put it on with acetic acid, put the acetic acid on as a pre-treatment. And I don't know if we formed a zinc acetate. I'm sure we probably did. And then we painted it, and I can go back, it's now 30 years since Matthew did his Eagle Scout project. And they repainted some of these things, but it wasn't because there was any paint flaking off. In fact, you can see where it's worn down to the zinc in 30 years on a handrail or something, and that stuff is on there, okay, because you have the right chemistry at the interface, okay. And I haven't gone in and do an Auger or an X-ray photoelectron spectroscopy. I haven't cut out a sample and taken it in to see if I've got a zinc carbonate or a zinc acetate there, but I think I have a zinc acetate. So you can do some things, and I think that's what we did. Either that or we just had wasted a couple of gallons of acetic acid. Big deal. But the scouts had fun, because give a scout a paintbrush and send them outdoors and where they can't do any damage, and can't even damage their clothes, right? I have a trailer that we use for campouts and things like that, and about every 10 years I buy the Rust-Oleum in the paint, and I tell the scoutmaster, okay, the scouts using this trailer, they're going to have to paint it with Rust-Oleum. It's outdoors. We don't care if they spill the green paint on the asphalt or anything. It's just paint, and hey, they love it. You know, I mean, 12-year-old boys, you know, spraying paint all over everywhere, spilling it all over. Who cares? Anyway, so where was I? I was talking about this stuff. Oh, I was getting down to, we got to galvanized pipe because people wanted something that was, they learned lead was toxic. They got to galvanized before World War II, and you still had to replace it every 20 or 30 years. Still used it in the Midwest, where in some waters it'll last for 40 or 50 years. They went to copper and brass, much more expensive, but can last forever. I mean, I just had some, what was probably turn plate. I had some flats on some windows that I had outside my bedroom in my house, which is 85 years old. They had some, it was just steel, it had been there for about 85 years. And just a year ago, I had that, it was starting to show a little rust. I think it was probably turn plate, okay? Because back in 1930, during the Depression, you could buy all the turn plate you wanted, and it was steel, and it was lead, a thin layer of lead would protect it. Well, they're gonna, for $5,000, they were gonna replace that for me, and they're gonna put in plastic. Well, you know what I think of plastic and UV rays from the sun. I don't trust it. So I had them put in copper, okay? Don't tell me in my neighborhood, because some night someone's liable to come by and rip the copper off, but copper has excellent corrosion resistance. The price went from $5,000 to $9,000 to go from, you know, replacing this flat part of the roof with plastic to replacing it with copper. Copper's not cheap, okay? But it has very good corrosion resistance in the atmosphere and stuff. And then they went to trying to save money, they went to PEX tubing, which is this stuff. And they basically had to cross-link it. I was telling you at the end of the day yesterday. They had to cross-link it, and PEX A is electron beam cross-linked. Why do you need to go to electron beams to cross-link? Turns out they do the same thing when they're making sandpaper, okay? You know, sandpaper is this paper, and they put some glue on it, and they put some sand on that, and they want to glue the sand to the paper. Well, there's no adhesive, if you take my welding lecture, there's no adhesive that sets up fast enough when they're running this sandpaper through the machine at about 50 miles an hour. Okay, it'll still be wet by the time you want to coil it. So they actually ran that paper in the sand through a electron beam. And the electron beam has enough energy to break the bonds, the primary bonds, in that adhesive and cause the adhesive to cross-link and set up within fractions of a second. So they can run it real fast. So people have been using electron beam cross-linking for dozens of years, and someone says, well, let's do that with polyethylene, and we'll use electron beam to cross-link it. And they came up with, about 25 years ago, PEX A. Some other people couldn't fight that patent, so they came up with a chemical cross-linking. That's not the easiest thing to do, because polyethylene is just carbon hydrogen. It's got the same formula as paraffin wax, okay? It's just paraffin wax is just a longer, even longer chain. Well, actually, no, it's not as long. So polyethylene is a longer chain hydrocarbon, but it's just carbon backbone with a bunch of hydrogens. Well, it turns out that both of them are used. Both of them, tests show they'll last for well over 100 years in corrosion. Okay, there are some other issues that people have run into, but it works extremely well. And the thing is, you can't do it. You could do it potentially, but you don't have enough energy in most cases. You could do it with ultraviolet light. Ultraviolet light will break down primary bonds. And I told you before, primary bonds are 1 to 3 electron volts. If I'm trying to break the bonds on a carbon backbone of polyethylene, I can't do it with something that only has a few tenths of an electron volt. And I don't know if what you remember from high school chemistry, or not high school chemistry, but maybe freshman chemistry. Energy is equal to h nu, Planck's constant times, and that, as I remember from my 3091, 40-some years ago, is equal to 12,400 over the wavelength in angstroms, which is equal to 1.24 over the wavelength in micrometers. Okay? Well, ultraviolet is anything below 0.310 micrometers, and so it means that the energy of ultraviolet is about 4 electron volts. Ultraviolet will break down primary bonds. Ultraviolet will give you a sunburn because it breaks down the primary bonds in your skin. You can go out there in the sun, and if you have something to protect you, transition lenses or something, you won't get sunburn if there's no ultraviolet light in the light spectrum. But there is ultraviolet in the sun. And so you break primary bonds. Okay, Dr. Belmar will be here tomorrow and Thursday, and I'll be here Monday.